In the final video here, we're going to be looking at the second order rate laws and how we get their integrated rate laws. Basically, how can we go from the kinematic rate law saying, so, okay, the rate of our reaction is dependent on this constant K times the concentration of some reactant of A squared. So if we find that this rate law to be true, how can we make a function that when we plug in a time, we can get a concentration at any point in our reaction? This is a pretty essential thing to studying rate of change or describing how reactants are changing over the time of a reaction. So in the lab, very helpful to know this stuff. So like we've done for every time, we're just going to use this idea of calculus where we say, okay, the change in concentration of A with respect to the change in time is equal to Ka squared, the negative of that, because we're decreasing our reactants through time. Okay, and then another step that I made was that, and I'm going to move this over just a little bit. Okay, so another simplification step that we made is, okay, well, if we take the, and I'm going to move actually the minus sign over now. Oops. If we make the rate of change infinitesimally small in its units of time, well, then we get this, okay? We get d concentration A over dt is equal to negative K concentration of A squared. Now, remember what we did in the last video. We have to take our concentration, and we have to move, and we treat this kind of like X would be, and we have to get it on the side with the very small change of concentration, and we have to get dt with our constant K. So let's go ahead and just do that quick. I'll make my color back to green here. So 1 over, oops, A squared, very small change in the concentration of A, is equal to negative K dt. So this is kind of interesting. It looks just the same, and in fact, the integral is actually a lot simpler. There's no ln's. It's just, this would be a to the negative 2. So in calculus, you add 1 to the power, divide by that. So this would be negative, and sorry, let me denote that we're taking the integral here. That's kind of important. So we take the integral of both sides. And what we're going to find for this is that we're going to get negative concentration of A to the negative 1, or in this case, negative 1 over concentration A is equal to negative KT plus, remember that arbitrary constant C. I think I explained the arbitrary constant, right? This gives us a family of these different function curves. Well, when given that derivatives get rid of constants, we don't know what that constant could have been. It could have been 0. There could have been no constant, but there could have been a shifting constant that we just don't know about. So we do have to solve for C, and it actually turns out that that is our initial concentration. So, but let's go ahead and solve for this. So we're going to move that negative over. We're going to get 1 over A equals KT, and then we're going to say minus C. Sorry, I had a brain fart there. Don't you love when those happen? And to solve for C, what we're going to do is we're going to set time equal to 0. So when we set time equal to 0, K drops out, negative C, so this really becomes C is equal to negative 1 over the initial concentration at time 0. So this is A sub naught, or in this case we're going to say A sub I. is equal to C. Okay, so what this will end up turning into is 1 over A is equal to KT plus 1 over that initial concentration. If you want to make this a, like, you know how functions are usually formatted as y as a function of x? Well, we can do the same thing where our y is a. You don't solve equations. You don't say, oh, 1 over y is equal to mx plus b. No, you say y is equal to mx plus b. But in this case, it does something different to our equation. So we're going to reciprocate everything. 1 over concentration A is actually equal to the concentration of A. And all you have to do is reciprocate everything. So 1 over KT plus our initial concentration. So that's where we get the second rate law. You'll see it one of two ways. And same with the last one. You'll either see it in that ln form or that simplified form. I like the simplified form. It's a lot easier to solve. But granted, if you need to find k still for whatever reason, and maybe have everything, you know, you can use it this way to find k, or you can use it this way to just have a function that you can plug something t into to get a concentration out. So I hope that this series has been helpful. I tried to explain it for all students, those who are just learning. Although if you're just learning chemistry, you probably haven't taken calculus, and that can be such a pain. I know, it's just like, I don't understand what's going on. Trust me, the math works out. I just wanted to show the math for those who are in differential equations, calculus, that kind of thing. But if you're curious, hey, now you know. Now you know where these things come from. So hope you guys enjoyed this video. If you did, please drop a like, comment, and subscribe. I would greatly appreciate it. And I hope that you have a wonderful day. Bye-bye.